Alright, welcome back everyone to our third and final video here in section 3. In this video we're going to be tackling products and quotients, right? So we're going to get this thing called the product rule and the quotient rule, and the claim is that these things are more complicated than maybe we would initially expect. So let's go ahead and take a look here. Suppose, again, we have two functions, but now we want to take the derivative of them being multiplied together, right? Look at this example down here. We have a function times another function, and we want to be able to take the derivative of this thing. Well, as you would hope, right, you would think that it would be maybe f prime of x times g prime of x, right? That would be the hope, but sadly it is more complicated than this. So if you try calculating this out, unfortunately it is not correct. However, it is the derivative of the first, f prime of x, times the second, g of x. So notice that there's no prime here, plus the first times the derivative of the second. So this one has an f prime, this one has a g prime, and then kind of there are bits where you don't do anything to the function. So like I said, this is a little bit more complicated than the product rule for limits, for instance, or the sum rule for derivatives, right? This is kind of unexpected. All right, and now the second part of this is if I wanted to take the derivative of a quotient of two functions. So here's my nice Leibniz notation, d dx, of this quotient of two functions, and here's my prime notation. All right, what do we do in this case? Well, we're going to have the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. And so you can see these things are kind of friends here. Kind of instead of this addition, we have the subtraction, but then it's even more complicated than that, right? This one's so complicated, in fact, that I've heard kind of, not quite a rhyme, but kind of a way to memorize this, right? So if you call this low, and you call this the high function, right? So the low function and the high function. Then I've heard before low d high, so d would be derivative of high, minus high d low, all over low squared. And I thought this is, pretty clever. Again, low d high minus high d low all over low squared. So this is a good way to memorize this quotient rule, right? And so that you don't accidentally mix it up. Because certainly if you take kind of this and you get it in the opposite order, then you won't get the same result, right? So it does matter, right, which number you subtract from the other number. Okay, let's see how we can apply this to a couple of examples here. Differentiate, again, this is now a product of two functions, right? So here's one function, here's another one. You can see that we're going to need a few things, right? So we need the derivative of this first function, we need the derivative of the second function, but we also need to remember kind of what those original functions were. So I'm going to go ahead and calculate out these derivatives. So I'm going to go ahead and write d dx, right? This thing doesn't really have a name, so I'm just going to do d dx of x squared. And now kind of getting ready to take the derivative of this thing, let me go ahead and write it as 3x to the negative 1 power, right? So when you divide by x to the first power, it's the same thing as multiplying by x to the negative 1 power. All right, that's going to help me with this bit right here, right? So the f prime, derivative of the first one. Let's go ahead and calculate this out. I'm going to have 2x minus 3, right? So remember this negative 3 is just along for the ride. That's the constant multiple rule. And then let's see, taking the derivative of x to the negative 1. So the negative 1 is going to come down, and then I'm going to get x to the negative 2 power, right? Reduce my power by 1. And we can see maybe these two negatives kind of cancel out. Let me go ahead and rewrite this one more time. 2x plus 3x to the negative 2 power. So that's the derivative of the first one. Now let's go ahead and take the derivative of the second one. So again, kind of rewriting this, I'm going to do x to the 1/2 power, right? Instead of square root, x to the 1/2 plus x plus 3. All right, the 1/2 is going to come down. I'm going to have x to the negative 1/2 power once I reduce my exponent by 1, plus 1 plus 0, right? Because the derivative of x is just 1, right? There's a secret 1 right here, thinking about its slope. And the derivative of 3 is 0. All right, let's go ahead and rewrite this one more time. 1/2 x to the negative 1/2 plus 1. Okay, now that I have these derivatives, basically it's just putting these things in the right spots. So, okay, I'm going to take the derivative of the first one. So in this case, we have 2x plus 3x to the minus 2 times the second one, times g of x. So that's this bit right here. So times root x plus 3. So notice this is not the derivative. This is just the original. Plus the original f. So the original f, well, that's going to be this right here. X squared minus 3 over x times the derivative of the second. So here's our second function. We know what its derivative is. We did that already down here. So that's going to be 1/2 x to the negative 1/2 plus 1. And so this right here is my derivative function. When it comes to writing answers for your homework, for quizzes, for exams, actually this is, kind of where we want you to stop. This is a lot easier to grade than if you start trying to simplify all of these things down, because I can kind of clearly see where each one of these pieces are coming from. So in fact, we don't want you to simplify at all. Okay, so there is an example of the product rule. Now let's go over an example, of the quotient rule, right? So in this case, we want to find the equation of the tangent line to this curve at a point 1, 1. And so the curve here, we can see it is a quotient of two functions. So I'm going to need to take the quotient rule in order to figure out the derivative of this thing. But remember, nowhere in here does it say take the derivative, right? So this is some alternative language here. But we need to remember, right, the equation of the tangent line looks like y minus f of c equals f prime of c times x minus c. In this case, we want the tangent line at the point 1, 1. So we're going to have y minus the function's value at 1, so that's going to be also 1, is equal to f prime of the x value here is 1 times x minus, and again the x value here is 1. So when it asks for the equation of the tangent line, remember it has kind of, hidden in there that we want this quantity here. We want the derivative of our function, in this case, at the value 1. So that's why we need to take the derivative of this. All right, so again, let me kind of go ahead and rip this function in pieces. I'm going to do the derivative first of 2x, and this is just, right, a linear function. It's the same thing as 2x plus 0, so its slope, remember the derivative of slope, is just 2. And likewise in the denominator, the derivative of x plus 1, well, the slope of this function is 1. Or in fact, let me go ahead and show you that we can apply the power rule to this if you'd like. Well, the derivative of 1 is 0. But if you want to apply the power rule to this, we need to remember that this is x to the first power. And so the 1 comes down, and we have x to the 0th power. And so you need to remember anything raised to the 0th power is 1. So really this is 1 times 1, which is 1. So there's in fact a couple different ways that we can think about this. All right, now let's go ahead and apply this quotient rule. Remember, I want to figure out the derivative for this function and then evaluate it at 1. So, according to the quotient rule, let's see if we can remember it. We have low d high. So in this case, my low function is x plus 1. D high, well, the derivative of the high function is 2. Minus high, d low. So here is the high function times the derivative of the low function. So in this case, 1. All divided by low squared. So in this case, x plus 1 quantity squared. And so we can go ahead and verify that looking up here, low d high minus high d low all over low squared, and make sure that we did this correctly. So that is the derivative function. We want the derivative evaluated at a very specific point, at the point x equals 1. So I'm going to go ahead and plug in 1 now. And so when I plug in 1, let's see, I'm going to have 2 times 2 minus 2 times 1, really, all divided by, let's see, 2 squared. Let's go ahead and evaluate this. So I'm going to have 4 minus 2 will be 2 on top. 2 squared will be 4. So this is going to give me the value 1/2. All right, so that is the derivative at the x value 1. So I go ahead and I plug this in. I'm going to have y minus 1 is equal to 1/2 times x minus 1. And that right there is my final answer. That is an equation of the tangent line to this function at the point 1, 1. If you can't resist, right, you can certainly distribute and resimplify and solve this y equals. Again, I wouldn't say it's required because it's a lot easier for me to grade this, right? I can kind of see what your slope is. I can see what point, right, what is your c value and f of c value. So it's actually more convenient for me to grade something like this. But again, if you'd like to solve y equals, you certainly can. Just make sure you don't make a mistake, right? That would be a shame. All right, that is the end of section number 3. Next time, we're going to get to everyone's favorite stuff, right? Trig functions. So that's going to be section number 4. I'll see you then.